Hi everyone! Hiding Expo B and Expo 3, we can factor it easily, as in video 19. With this principle, let's memorize and make formulas easily. This is an example. Taking Expo B and A, call this the skeleton of double 11 formula. It has 0AB in the middle and skeleton 11. If you want to verify it, multiply it as if primary arithmetic. The shifted sum makes double 11. You'll use this formula later. You already know 11 squared is 121. 11 cubed, 1331. 11 to the 4, 14641. These are the skeletons of binomial expansions, known as Pascal's triangle. Even forgetting them, you can get them easily. Like 121 times 11. Shifted sum makes 1331. Once again, 1331 times 11. The shifted sum, 14641. Just verify yourself. In ternary, they are the same. 1000 is 1000. But in A over binary, they are different. Move on to Expo -1. Alternate plus and minus. Let me call this Hinge. Now, given Expo 2, to both sides, the equality still stands. If you know this formula, you can get the hinge of that formula. From 11 cubed formula, hinge 11 cubed formula. Move on to the terminal difference formula. Like all 1 times 9 is all 9, all 1 times hinge 11, 100 minus 1, 1000 minus 1. These are the skeletons of the terminal difference. A minus B times all 1. Memorize this way. Minus with minus, plus plus plus. Minus with minus, all plus 1. Minus with minus, all plus 1. Can you factor this? Minus with minus, all plus 1. I'll expand this. Times hinge 11, the shifted sum leaves only the terminals. 5-digit, 4th degree. To this cubic terminal difference, giving hinge, we get cubic terminal sum that you might already know. They are the hinges of each other. Next formulas. Hinge all 1 times 11 is terminal sum. Even digit, odd degree. A plus B times hinge all 1. Memorize this way. Sum with sum, plus minus plus. Sum with sum, hinge all 1. Sum with sum, hinge all 1. Can you factor this? Sum with sum, hinge all 1. I'll expand this. The shifted sum leaves only the terminals. 6 digit, 5 degree. What about even power? They need I or a square root to factor. Go to video 28 and 40. They don't have sum. Times hinge all 1 makes terminal difference. Verify yourself. Practical example. A factorization from a high school admission test here in Japan. Look for a homogeneous part, which means separate 4th degree parts from cubic parts. They have a common factor, if factorable. It's double 11 formula. 11 times 101. The terminal difference also has 101. Common factor 11. Double 11. Hinge 11 and 1. It's done. Here is a reminder. Different digit skeletons cannot be added. Only 5 digit 4th degree. Cubic parts disappear. Next example, also from a high school admission. 2nd degree. Also 2nd degree, so 3 digit only. Their skeletons. 2, 2 with negative. We can add them. And hiding only x, you can factor it. It's done. I just leave a standard solution. Next example is an expansion, also from a high school admission. Hinge pair 1 to 1. Mirror hundreds. 122. Hinge 122. Hinge product. Many zeros. It's done. A standard solution. Hinge product formula often works. Okay, let's move on to the drill. Okay, thank you for watching. See you next time. Bye.